Hello everyone. Today we are going to learn Chapter 2 Pressure, particularly in subtopic 2.1 Pressure in Liquid. Before further lesson, let's look at the learning outcome first. For today's lesson, we cover only one learning outcome, which is communicate about the concept of pressure in liquids, which is P equal to H rule G. The content in the concept of pressure in liquid that we are going to learn is what is pressure, characteristic of pressure in liquid, and relating pressure in a liquid to the depth and density of the liquid. So, what is pressure? Generally, pressure is defined as perpendicular force per unit area acting on a surface. Mathematically, we can state that P equal to F over A. The SI unit of pressure is the Pascal or Newton per meter square. This is because pressure equal to perpendicular force. The SI unit force is Newton. Per area, the SI unit of area is meter square. So, we can get Newton per meter square. Actually, 1 Pascal equal to 1 Newton per meter square. Characteristic of pressure in liquid. Pressure at any point in a liquid is due to the weight of the liquid acting on the surface area of that point. As shown in figure, there is a surface area inside the liquid and the pressure on that surface area is due to the weight, which is actually a force acting on that surface area. For example, we have a small cube inside a beaker containing a liquid, like this. So, a small cube inside the liquid experiences the pressure, and that pressure is caused by the weight of the liquid pressing on the surface of the cube. Next, liquid always finds its own level. What does it mean? It means at the same depth, the liquid pressure must be the same. Otherwise, the liquid will move until the pressure will equalize. For example, there is a tube with the same depth for both sides containing water. So this is a tube with tap closed. If we open the tap, the water will flow until the pressure for both sides are same, thus making the water level for both sides are equal. Because the water can flow, so it will flow until the pressure for both sides are same. Thus, when the pressure are same, so the water level also same. Now, the characteristic of pressure in liquid in terms of shape, size, and area. The pressure in liquid does not depend on the shape, size, and area or surface area of the container. For example, we have a Pascal vessel. This is a Pascal vessel. As you can see, both tubes have different size, shape, and also the surface area. When a liquid such as water is poured into the Pascal vessels, which have the same depth, the height of the water level in all tubes are identical because the pressure at point A, B, C, D, and E are same, even though all tubes have different shape, size, and surface area. That is why the pressure in liquid does not depend on the shape, size, and surface area. Pressure in liquid depends on vertical depth. There are two tubes. One is vertical and the other one is slightly slanted. So, this is two tubes with a same height of water, which is the H, actually the depth. Then, this is the length of water column. We label it as L1 and this L2. The length of water column in vertical tube, which is L1, is shorter than the length of water column in slanted tube, which is L2, as you can see in the figure. However, the vertical depth, which is height of water in both tubes, are identical. Since the water in both tubes have same vertical depth, it shows that pressure at point A and B are same, even though the length of the water column in both tubes are different. Therefore, pressure is depend on vertical depth but not on length of the water column. Pressure in liquid at the same depth acts equally in all directions. There is a tin filled with water. As you can see, similar holes at the same height are made on the side of a tin. These holes are plugged out. On removing the plugs, it is found that water jet from all holes spurt out equally fast and reach the same distance away from each hole. This shows that the pressure at the same depth of any point in a liquid act equally in all directions. Pressure in liquid increase with depth. 3 holes are made at a different height on a side of a tall vessel. This is a vessel. These holes are fitted with side tubes which are plugged up and the vessel is filled with water. As we know, the higher the height of the hole made means that the deeper that hole inside the water vessel. Then, when removing the plugs, it is found that water spurts out furthest and fastest from the lowest hole than the other 2 holes. As shown in figure, the water spurts out from the lowest tube have a longer distance compared to the medium and upper hole. This shows that as the depth increases, the liquid pressure also increases. Pressure in liquid increases with density. One tin is filled with water while the other is filled with cooking oil. A hole made at the same height on the side of each of 2 similar tins. As you can see in the figure, the density of water is higher than the cooking oil. So, the density of water is 1 gram per centimeter cube, while the density of cooking oil is 0.93 gram per centimeter cube. Then, it is found that the jet of water falls further from the tin and flow faster than the jet of cooking oil, although both tins contain equal amounts of water and oil. This shows that pressure in water is higher than pressure in cooking oil. Therefore, the pressure in a liquid increases with the density of liquid when the density of liquid is increased. So now, relating pressure in a liquid to the depth and density of the liquid. Consider a cylindrical container with liquid of height and cross-sectional area which is filled with a liquid of density. So this is a cylindrical container with a liquid. We can see the height, or actually the depth of the liquid, and the surface area, also the density of the liquid. So the pressure in liquid, for example at point X, is, first we know that the pressure is actually the force per unit area. So the force on point X is weight of the liquid acting on the surface area. So the weight of the liquid is a mass of the liquid. Then force equal to the mass times the gravitational field strength. The gravitational field strength we need to consider in order to find the pressure in liquid. Then substitute the force with the mg per A. Next, mass of liquid in the container is actually equal to the volume times the density, because we know that the density of the liquid is equal to the mass over volume. So mass, or M, equal to the V rho. Then we can substitute the mass with the V rho G per A. The volume of liquid in the container is actually the surface area times the depth. So V equal to the AH. Then substitute the V with the AH rho G per A. Then simplify the formula. Hence we can get pressure in liquid is equal to the depth times density times the gravitational. So still remember that the pressure in liquid does not depend on the surface area, but it increases with the depth and density. So this formula shows that the pressure in liquid proportional to the depth and also the density. Using this formula, we can calculate or solve the problems regarding the pressure in liquid. Before we end our lesson, let's do some quick exercise to test ourselves. So, first question is, pressure at any point in a liquid is due to the answer is due to the weight of the liquid acting on the surface area. Second question, does pressure in liquid at the same depth act equally in all directions? So the answer is yes. Next is, pressure in liquid does not depend on. So the pressure in liquid does not depend on the shape, size and area or surface area of the container. The last question is, pressure in liquid increases with increase with the depth and density. As we just learned just now, the pressure in liquid is proportional to the depth and also the density. So that's all for today.